And now in this lecture we'll answer two questions. In the first question we'll find out the area of this big circle, and in the second question we'll find out the area of this rectangle ABCD using two different methods. So we start with the first question. In the drawing we have two circles that are tangent to each other at this point C, or we have two circles that touch each other at point C, and we also have this is tangent DE that is tangent to this circle at this point B, and tangent DE is tangent to the big circle at this point. And in addition, we know that this is line segment AC that is equal to 6 units in its length. This is line segment CB that is equal to 9 units in its length. Again, our mission is to find out the area of this big circle. Okay. So first of all, we define the point of tendency of tangent DE with this big circle. This point is point M. And we'll focus on this common external point, point B. Point B is the common external point in relation to this big circle. So from this common external point, point B, we have here tangent BM that is tangent to this big circle at point M. In addition, from the same common external point B, if we draw this straight line, it will cut the circle at 2 points. Point C, it will cut the big circle at 2 points, point C and point A. In this way we create chord CA. And therefore we can implement here rule 10. So we click quickly on rule 10. Rule 10 is true in any circle. In any circle, if AB is any chord, here AB is a chord in this circle, and PT is a tangent to this circle at point D. So in this drawing, the following equation is true: that PT square equals to PA times PB. Again, PT square equals to PA times PB. We can implement rule 10 in our drawing. Why? Because in our drawing, if we focus on this common external point, point B, from this common external point, point B, we have tangent BM, and from the same common external point B, if we draw this straight line, it will cut the circle, the big circle, to point C and A. In this way, we created chord CA. So all the requirements of rule 10 are satisfied, and therefore we can implement rule 10. According to rule 10, the following equation is true: that BM square equals to BC times BA. Again, BM square equals to BC times BA. So I write it down. So if we focus on the common external point, point B, according to rule 10, the following equation is true: that BM square equals to BC times BA. So repeat again. If we focus on the common external point, point B, according to rule 10, the following equation is true: that BM square equals to BC times BA. Okay. BM is the missing tangent, so we leave it as it is, so it is BM square, and it is equal to BC. BC is 9 times BA. BA in total equals to 16 plus 9, that is 25. Again, BA in total equals to 25. So according to rule 10, we found out that BM square equals to 9 times 25. Here we take a root out of this equation, and we get that BM equals to the square root of 9, that is 3, times the square root of 25, that is 5. So in total, if we found out that Vm equals to 3 times 5, that is 15. Vm equals to 15 units in its length. So this is Vm, tangent Vm, that is equal to 15 units in its length. In the next step, from point C, that is the point of tendency of the two circles with each other, we will draw a straight line towards tangent NB. And we will define the point of tendency. We define the touching point of tangent C with side NB. This point is point M. Okay, so here in the next step we will focus on this common standpoint, point N. From this common standpoint, point N, we have two tangents to this circle, tangent NC and tangent NB, and according to rule 2 they are equal to each other. That is to say, NC equals to NB. NC equals to NB. Okay, so repeat quickly rule 2. According to rule 2, the length of two tangents from a common standpoint to a circle are equal. In the drawing we have a circle, and this is the common standpoint, point P. From this common standpoint, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So here, we can implement rule 2. If we focus on this common standpoint, point N, from this common standpoint, point N, we have two tangents to the small circle, tangent NB and tangent NC, and according to rule 2, they are equal to each other. That is to say, NB equals to NC. So I write it down. NB equals to NC according to rule 2. In the next step, I will copy this triangle C and B in a new page, and we will analyze this triangle C and B. Okay, this is triangle C and B that I covered from the original drawing. This triangle C and B, side CN equals to side NB. And we have the rule that says that in front of equal sides in the triangle there are equal angles. So in front of this side CN we have this angle, and in front of this side VN we have this angle. And those two angles that are located in front of those two equal sides must be equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to the rule that I mentioned. Okay, so we found out that this angle equals to alpha, and this angle also equals to alpha. In the next step, we join point C and M together by a straight line. And we continue to focus on this common standpoint, point N. From this common standpoint, point N, we have two tangents to the big circle, tangent NM and tangent NC. And according to rule 2, they are equal to each other. That is to say, NM equals to NC. So in the next step, I copy the right triangle, it is not a right triangle CMN in a page, and we analyze this triangle CMN. So actually, this is triangle CMN that I copied from the original drawing. In this triangle CMN, side CN equals to side MN. In front of this side CN, we have this angle. In front of this side MN, we have this angle. And because of the fact that those two angles are located in front of equal sides, they must be equal to each other in their sizes. So if we define the size of this angle as beta, then this angle must be also equal to beta according to the rule that I mentioned. According to the rule that states that in front of equal sides in the triangle are equal angles. So if we found out that this angle equals to beta, and this angle also equals to beta. In the next step, I'll copy this big triangle CMB in a new page, and we'll analyze this triangle, the big triangle CMB. So actually, this is triangle CMB that I copied from the original drawing. We know that the sum of the angles in any triangle is equal to 180 degrees. It is true in any triangle, and especially it is true in this triangle CMB. So the sum of the angles in triangle CMB is equal to 180 degrees. So which angles we have in triangle CMB? We have, this is angle alpha, plus this is angle beta, plus this is angle alpha plus beta. So in total, the sum of those three angles must be equal to 180 degrees, according to the rule that I mentioned. So in this side of the equation, we have alpha plus alpha, that is 2 alpha, plus beta, that is 2 beta, and it is equal to 180 degrees. So if you found out that 2 alpha plus 2 beta equals to 180 degrees. Here we will divide this equation by 2, and finally get that 2 alpha over 2 is alpha, plus 2 beta over 2 is beta, and it is equal to 180 degrees over 2, that is 90 degrees. So in total, we found out that alpha plus beta equals to 90 degrees. So this is the big angle alpha plus beta. So actually it is angle MCB. Angle MCB equals to alpha plus beta, and alpha plus beta equals to 90 degrees. So alpha plus beta, it is a right angle. That is to say, we actually found out that angle MCB is a right angle. We know that AB is a straight line. According to what is given us in the question, AB is a straight line. So if we focus on the left side of this straight line AB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So let's take rule 3. According to rule 3, the sum of the angles on one side of a straight line is equal to 180 degrees. AB is a straight line. So if we focus at point Q, on the upper side of the straight line AB at point Q, so here the sum of the angles must be equal to 180 degrees according to this rule 3. So which angles we have at the upper side of AB point Q? We have this angle alpha plus beta. So according to this rule 3, alpha plus beta equals to 180 degrees. So we can actually implement rule 3 in our drawing. If we focus on the left side of the straight line AB at this point C, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the left side of the straight line AB at point C? We have this angle that is a right angle, plus this missing angle. In total, they must be equal to 180 degrees. And therefore, this missing angle must be equal to 90 degrees in its size. According to rule 3, this missing angle must be equal to 90 degrees in its size. In the next step, we join points A and M together by a straight line. And we focus on the big circle. So inside this big circle, we have peripheral angle ACM. This is peripheral angle ACM, and the size of this peripheral angle ACM is equal to 90 degrees. Why? Because angle ACM equals to 90 degrees. So inside the big circle, we have peripheral angle ACM that is equal to 90 degrees in its size. And according to rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. That is to say, this is peripheral angle ACM that is equal to 90 degrees, and therefore this peripheral angle ACM must subtend on the diameter of the circle. Peripheral angle ACM subtend on AM, and therefore AM must be the diameter of the circle, according to rule 5. So I take rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees must subtend on the diameter of the circle. So here we have, this is peripheral angle MAB, that is equal to 90 degrees in size, and therefore this peripheral angle MAB must subtend on the diameter of the circle. That is to say, MN is the diameter of the circle. So as I mentioned, we can implement rule 5 in our drawing. Why? Because in our drawing, we have peripheral angle ACM that is equal to 90 degrees inside, and therefore peripheral angle ACM that is the right angle must subtend on the diameter of the circle. Peripheral angle ACM subtend on AM, and therefore AM must be the diameter of the circle. According to rule 5, AM must be the diameter of the circle. So we found out that AM is the diameter of the circle, of the big circle, according to rule 5. But we also know that the center of any circle must be located on the diameter of the circle. And therefore, the center of this circle must be located on the diameter AM of this circle. So, this is point O. That is the center of the circle. Why? Because of the fact that the center of the circle must be located on AM, that is the diameter of the circle. You can see here that point O is indeed located on AM, that is the diameter of the circle. So actually, point O is the center of the circle, point M is a point on the circle itself, therefore OM is the radius of this circle. We define the radius OM of this circle as R. So OM is the radius of the circle, that is equal to R. And because of the fact that the radius OM that is equal to R, the radius OM is drawn to point M, that is the point of tendency of tangent DE with this big circle. And whenever you have a radius that is drawn to the point of tendency, then according to rule 1, tangent DE will be perpendicular to the radius MO. Again, because of the fact that the radius OM is drawn to point M, that is the point of tendency of tangent DE with this big circle, and whenever your radius that is drawn to the point of tendency, then tangent DE will be perpendicular to the radius MO according to rule 1. If DE is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Okay, so here we have the right triangle A and B. So in the next step, I'll copy this right triangle A and B in a new page, and we'll implement the Pythagoras theorem on this right big triangle, triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is a promotion for Pythagoras theorem. The hypotenuse AB, in total it is equal to 16 plus 9, that is 25. So actually, this is the right triangle A and B that I copied from the original drawing. MB equals to 15 units in its length according to rule 10. AM is the missing side. So according to the Pythagoras theorem, in this right triangle A and B, AB squared, that is the square of the hypotenuse, equals to AM squared plus MB squared. So I write it down. AB squared, that is the square of the hypotenuse, is equal to AM squared plus MB squared. AB is 25, therefore AB squared is 25 squared, that is 625, and it is equal to AM squared. AM is the missing side, so we leave it as it is, plus MB squared. MB is 15, therefore MB squared is 15 squared, that is 225. So in total, according to the Pythagoras theorem, I should find out that in the right triangle A and B, $625 equals to AM squared plus 225. Here we subtract 225 from this equation, and we get that 625 minus 225 is 400, so 400 equals to AM squared. So here we take a root out of this equation, and finally we get that the missing side AM is equal to the square root of 400, that is 20. AM equals to 20 units in its length. AM is one side of triangle AMB, but AM is also the diameter of the big circle. We have already found out that AM is the diameter of the big circle. Here, AM is the diameter of the big circle. Okay. If AM is the diameter, it means that the radius must be equal to half of it. So actually, the radius R of the big circle must be equal to the diameter AM over 2. AM is 20, therefore the radius must be equal to 20 over 2, that is 10. So if you found out that the radius of the big circle is equal to 10 units in its length. I repeat again, the radius of this big circle, R, equals to 10 units in its length. Our mission is to find out the area of this big circle. Actually, we know that the area of any circle, is equal to pi times the radius of the circle squared. And therefore, the area of the big circle must be equal to pi times the radius of the big circle squared. So it is pi times the radius of the big circle, that is 10 squared. So it is pi, 10 squared is 100. So if you found out the area of this big circle equals to either 100 pi square units, or in terms of numbers, it is equal to 314.159 square units. Again, we should find out that the area of this big circle equals to either 100 pi square units, or in terms of numbers, it is equal to 314.159 square units. So we finish with the first question. In the next step, we'll find out the area of this rectangle ABCD using two different methods. So, we'll start with the first method. In the drawing, we have rectangle ABCD. We know that this is line segment AM, that is equal to 5 units in itself. In addition, we have here this semicircle. Again, our mission is to find out the area of this rectangle ABCD. Again, we start with the first method. ABCD is a rectangle, and therefore all those four angles that inside rectangle ABCD are right angles. So actually, this is a right angle. This is also a right angle. This is a right angle. And finally, this is also a right angle. In the next step, we define the center of this semicircle. This point is point O. We define the radius of this semicircle as x. So point O is the center of the semicircle, point A is the point of the semicircle itself, therefore OA is the radius of this semicircle, that is equal to x according to our definition. we define the point of tendency of tangent DC with this semicircle. This point is point E. In the next step, we join points O and E together by a straight line. Point O is the center of the big semicircle. Point O is the center of the semicircle. Point E is the point of the semicircle itself. Therefore, OE is the radius of the semicircle. It is equal to x according to our definition. OE equals to x according to our definition. So here the radius OE is equal to x. The radius OE is drawn to point E, that is the point of tendency of tangent DC with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius EO. If DC is perpendicular to DO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So inside quadrilateral ADEO, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral OADE, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this rectangle plus a square. So we relate to this quadrilateral OADE, it's a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle OADE, side OE must be equal to the opposite side DA. But OE is x, therefore DA must be also equal to x units in its length. In the next step, we join points O and M together by a straight line. Point O is the center of the semicircle. Point M is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, OM is the radius of this semicircle. It is equal to x. In the next step, we define this side of B as A. We define this side MB as B. And we implement the Pythagoras theorem on this right triangle, triangle OMB. So I copy this right triangle OMB in the new page and we implement the Pythagoras theorem on this right triangle, triangle OMB. According to the Pythagoras theorem, in any right triangle, the square they are produced equals to the sum of the squares of the perpendiculars. Here by PT is the progression for Pythagoras theorem. So actually, this is the right triangle MBO that I copied from the original drawing. According to the Pythagoras theorem, this right triangle MBO m all squared, that is the square of the hypotenuse, equals to mb squared plus b all squared. So I write it down. M all squared, that is the square of the hypotenuse, is equal to mb squared plus OB squared. The hypotenuse OM is x, therefore OM squared is x squared, and it is equal to OB squared. OB is a, therefore OB squared is a squared, plus MB squared. MB is b, therefore MB squared is b squared. So in total, according to equation 1, we actually found out that x squared equals to a squared plus b squared. Again, according to equation 1, we found out that x squared equals to a squared plus b squared. In the next step, I'll copy this right big triangle MB in a new page, and we'll implement the Pythagoras theorem on this right big triangle AMB. It's actually triangle OMB. So actually, this is the right triangle OMB that I got it from the original drawing. According to the Pythagoras theorem, in this right triangle OMB, OM squared, that is the square of the hypotenuse, equals to MB squared plus B all squared. So I write it down. This will be equation 2. OM squared, that is the square of the hypotenuse, is equal to MB squared plus OB squared. The hypotenuse OB equals to x units in its length, therefore the hypotenuse OM equals to x units in its length, therefore OM squared is x squared. Actually, this is triangle A and B. This is triangle A and B. This is the right big triangle A and B. Side AB in total equals to x plus a. Okay, side AB equals to x plus a in total. So actually, this is side AB, that is equals to x plus a. The hypotenuse AM equals to x, and MB equals to b. So OM is x, so AM is x, therefore AM squared is x squared, and it is equals to MB squared. MB is b, therefore MB squared is b squared plus AB squared. Plus AB squared. AB is x plus a, therefore AB squared is x plus a squared. So in total, according to the Pythagoras theorem, in this right triangle A and B, we found out that x squared equals to b squared plus x plus a squared. This is according to equation 2, so we found out that x squared equals to b squared plus x plus a squared. X plus a squared equals to x squared plus a squared plus 2 times a times x. Okay, so here we have b squared plus a squared, and according to equation 1, b squared plus a squared equals to x squared. Okay, so we substitute b squared plus a squared in this equation 2 by x squared from this equation 1. And we get that actually I did a mistake here because AM equals to 5 units in its length. The opposite AM equals to 5 units in its length, therefore AM squared is 5 squared, that is 25. AM squared, AM is 5, therefore AM squared is 5 squared, that is 25. AM squared is 25. It is not x squared, but it's 25. Again, AM squared is 5 squared, that is 25. So in this side of the equation we have 25. So here we have 25 equals to b squared plus a squared is x squared according to equation 1. So we have x squared plus x squared plus 2ax. So according to equation 2, we found out that (25) equals to x squared plus x squared plus 2a. So according to equation 2, we found out that 25 equals to x squared plus x squared is 2x squared plus 2a. Here we divide this equation by 2, and finally get that according to this equation 2, 25 over 2 is 12.5. 12.5 equals to 2x squared over 2 is x squared. This is 2ax. And 2ax over 2 is ax. So we found out that according to equation 2, 12.5 equals to x squared plus a squared. So according to equation 2, we found out that 12.5 equals to, here we take x, we take out x as a common factor from those two expressions. So inside the brackets we left with x plus a. So in total we found out that according to equation 2, x times x plus a equals to 12.5. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? The area of rectangle ABCD is equal to the length of the rectangle times the width. It is true in any rectangle, and it is especially true in our rectangle ABCD. So it is the length times the width. The length of this rectangle ABCD is AB times the width. The width is dA. So in total we found out that the area of rectangle ABCD equals to AB times dA. AB is x plus a times dA. dA is x. So in total we found out that the area of rectangle ABCD d equals to x times x plus a. But according to equation 2, x times x plus a equals to 12.5. Therefore, here x times x plus a equals to 12.5. So in total, we found out that the area of rectangle ABCD is equal to 12.5 square units. And that is the answer to the question. I'll repeat again. We found out that the area of this rectangle ABCD, that is the area that we are looking for in this question, it is equal to 12.5 square units. We finished with the first method. In the next step, I will present to you how to find out the area of this rectangle ABCD according to the second method. So first of all, we know that ABCD is a rectangle. So for all those four angles inside rectangle ABCD are right angles. This is a right angle. This is a right angle. This is a right angle. And this is also a right angle. In the next step, we define the center of this semicircle. This point is point O. We define the point of tendency of tangent DC with this circle. This point is point E. We have already found out and we define the radius of this semicircle as x. OA is the radius of the semicircle, that is equal to x according to our definition. In the first method, we have already found out that AD must be also equal to x. So I'll not repeat on it again. AD equals to x. In the next step, we define this point as point N, and we'll join points M and N together by a straight line. By doing this construction, we created here peripheral angle NMA. This is peripheral angle NMA, and peripheral angle NMA subtend on AN, that is the diameter of this circle. Again, peripheral angle NMA subtend on AN, that is the diameter of the semicircle. And according to rule 7, if a peripheral angle subtend on the diameter of the circle, it is equal to 90 degrees. So here we have peripheral angle ACB, that is subtend on CB, that is the diameter, that is subtend on AB, that is the diameter of this circle, and therefore peripheral angle ACB is equal to 90 degrees because of the fact that it is subtend on the diameter AB of this circle. So whenever you have peripheral angle that is subtend on the diameter of the circle, it must be equal to 90 degrees in its size. To this rule 7. And because of the fact that this is peripheral angle AMN, that is subtend on AN, that is the diameter of the circle, peripheral angle AMN must be equal to 90 degrees in its size. So this is peripheral angle AMN, that is equal to 90 degrees in its size. Okay, so in the next step, so we'll define line segment OB. This is line segment OB as A, and in the next step we'll prove that the right triangle AMN is similar to this right triangle AMB according to angle similarity rule. Repeat again, we'll prove that the right triangle AMN is similar to the right triangle AMB according to angle similarity rule. Actually, it is given us the question that AM equals to 5 units in its length. AM equals to 5 units in its length. So I copy this right triangle AMB and this right triangle AMN in a new page, and we'll prove that those two right triangles are similar to each other according to angle similarity rule. But before that, we define this angle, angle MAN as alpha. So in the right angle AMN, this angle equals to alpha, this angle equals to 90 degrees, and therefore this perpendicular angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, we focus on this right angle A and B. In this right angle A and B, this angle equals to alpha, this angle equals to 90 degrees, and therefore this perpendicular angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. AN is the diameter of the semicircle. The radius of the semicircle is x. Therefore, the diameter must be twice as big. The diameter must be twice as big as the radius. The radius is x, therefore the diameter must be equal to 2x. So AN equals to 2x units in its length. So actually, those are the two right triangles, triangle AMN and triangle AMB, that are coming from the original drawing. So in the next step, we prove that those two right triangles are similar to each other according to angle similarity rule. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So actually, this is angle MBA. In the right triangle AMB, and it is equal to this angle. This is actually angle AMN. In the right triangle, triangle AMN. They are both equal to 90 degrees, and therefore they are equal to each other. In addition, this is an angle alpha that is actually a common angle that belongs to both triangles. So I can write down that angle alpha equals to itself is a common angle that belongs to both triangles. So if you relate to angle alpha as it belongs to this triangle A and B, it will be defined as angle MAB. And if you relate to angle alpha as it belongs to this triangle AMN, it will be defined as angle MAN. So angle alpha equals to itself. This equation means that angle alpha equals to itself. So angle alpha equals to itself. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle AMB in the right triangle AMB, and this is equal to this angle. This is actually angle MNA in the right triangle AMN. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually prove that all the triangles in this right triangle AMB are correspondingly equal to all the triangles in this right triangle AMN. Therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. I should found out that this is the right triangle AMB, and is similar. This is the sign of similar to this right triangle, triangle AMN, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. But again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AM in the right triangle AMB over side AN in the right triangle AMN is equal to side AB in the right triangle AMB over side AM in the right triangle AMN. Repeat again. For the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. That side AM in the right triangle AMB over side AN in the right triangle AMN equals to side AB in the right triangle AMB over side AM in the right triangle AMN. AM is 5 over AN. AN is 2x and it is equal to AB. AB is x plus a over AM. AM is 5. So in total, according to equation 1, we found out that 5 over 2x equals to x plus a over 5. Here of course multiply this equation 1, and finally we get that 5 times 5, that is 25, is equal to 2x times x plus a. Here we divide this equation 1 by 2, and we get that according to this equation 1, 25 over 2 is 12.5, and 12.5 equals to 2x over 2 is x times x plus a. X plus a. So in total we found out that according to equation 1, x times x plus a equals to 12.5. Our mission is to find out the area of this rectangle ABCD. So actually the area of any rectangle is equal to the length of the rectangle times the width. And therefore the area of our rectangle ABCD must be equal to the length of the rectangle ABCD, that is AB, times the width, that is AD. So in total we found out the area of rectangle ABCD equals to AB times AD. AB is x plus a times AD. AD is x. So in total we found out that the area of rectangle ABCD equals to x plus a times x. But x plus a times x is 12.5 according to equation 1. So we substitute x times x plus a by 12.5. So in total we found out that the area of rectangle ABCD equals to 12.5 square units. So in both methods we arrived to the same result. We actually found out that the area that we are looking for in this question, that is the area of this First angle ABCD is equal to 12.5 units in both methods. So the next step, I'll summarize the lecture. Let's start with the first question. In the first question, our mission is to find out the area of this big circle. So in the drawing, we have two circles that are tangent to each other at this point C. In addition, we know that this is line 7AC, that is equal to 6 units in its length. This is line 7CB, that is equal to 9 units in its length. Again, our mission is to find out the area of this big circle. So first of all, if you focus on, this is point B, that is a common external point in relation to this big circle. So from this common external point B, we have tangent VM, and from the same common external point B, if you draw the straight line BC, it will cut the circle, the big circle at 2 points, A and C. So all the requirements of Rule 10 are satisfied, and therefore we can implement here Rule 10. According to Rule 10, the following equation is true, that BM square equals to BC times BA. Again, BM square equals to BC times BA. So repeat again. If we focus on the common external point B, according to Rule 10, the following equation is true, that BM square equals to BC times BA. BM is the missing sign, so many units it is, and it is equals to BC. BC is 9 times BA. BA in total equals to BC, that is 16, plus CB, that is 9. 16 plus 9 is 25. So BA in total equals to 25. So in total we found out that BM equals to 9 times 25. Here we took a root out of this equation, and finally found out that BM equals to the square root of 9, that is 3, times the square root of 25, that is 5. So in total BM equals to 3 times 5, that is 15. BM equals to 15 units in its length. In the next step, from this point C, that is the point of tendency between the two circles, we draw a straight line towards MB. We define the touching point of the straight line with side MB. This point is point N. Actually, CN is a common tangent that belongs to both circles. So here, if you focus on this common external point N, from this common external point N, we have two tangents to this small circle, tangent NC and tangent NB, and according to Rule 2, they are equal to each other. In the next step, I copy this right angle CNB in a new page and analyze this right angle CNB. This is right angle CNB that I copied from the original drawing. I found out that CN equals to NB. In front of CN, we have this angle. In front of NB, we have this angle. And because of the fact that those two angles are located between equal sides, they must be equal to each other. So if you define this angle as alpha, then the other angle must be also equal to alpha, because they must be equal to each other according to the rule that I mentioned. We continue to focus on this common external point N. From this common external point N, we have two tangents to the big circle, tangent NC and tangent NM. And according to Rule 2, they are equal to each other. That is to say, NC equals to NM. Okay, so in the next step, actually, we joined points M and C together by a straight line, and I copied this triangle CMN in a new page and analyze this triangle CMN. This is triangle CMN that I copied from the original drawing. CN equals to MN according to Rule 2. In front of this side CN, we have this angle. In front of this side MN, we have this angle. And because of the fact that those two angles are located in front of those two equal sides, they must be equal to each other and their sizes. If we define the size of this angle is beta, then this angle must be also equal to beta because they must be equal to each other. So, in the next step, I copy the right big triangle MCB in a new page and analyze this right big triangle MCB. So, actually, this is the big right triangle MCB that I copied from the original drawing. According to the rule that said that the sum of the angles in the triangle is equal to 180 degrees, that is to say, the sum of the angles in triangle MCB must be equal to 180 degrees. So which angles we have in the right triangle MCB? We have this angle that is alpha, this plus angle beta, plus this angle that is alpha plus beta. In total, it must be equal to 180 degrees. So in this side of the equation, we have alpha plus alpha, that is 2 alpha, plus beta, that is 2 beta. In total, it must be equal to 180 degrees. Here we divided this equation by 2, and finally found out that 2 alpha over 2 is alpha, 2 beta over 2 is beta. So alpha plus beta equals to 100 over 180 degrees over 2, that is 90 degrees. So in total, we should find out that alpha plus beta equals to 90 degrees. Actually, angle MCB is equal to alpha plus beta, and alpha plus beta is 90 degrees. So angle MCB is a right angle. We know that AB is a straight line. So if we focus on this side of the straight line AB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at this side of AB at point C? We have this angle that is the right angle plus this missing angle. In total, it must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. This is to say, angle ACM is a right angle. In the next step, we join points A and M together by a straight line. So, inside this big circle, we have this peripheral angle ACM, that is a right angle. And according to rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. So this peripheral angle ACM, that is a right angle, must subtend on the diameter of the circle. So peripheral angle ACM subtend on AM, and therefore, according to rule 5, AM must be the diameter of the circle. Okay, again, according to rule 5, AM is the diameter of the circle. Okay, AM is the diameter of the circle, and the center of the circle must be located on the diameter of the circle. So this is point O, that is the center of the circle, and you can see here that point O is located on AM, that is the diameter of the circle. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of this circle, big circle. And because of the fact that the radius OM is drawn to point M, that is the point of tendency of tangent DE with this circle, and whenever you have a radius that is drawn to the point of tendency, then tangent DE will be perpendicular to the radius MO. If D is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So in the next step, I copy the right triangle A and B in a new page, and we implemented the Pythagoras theorem on this right triangle A and B. This is the right triangle A and B that I copied from the original drawing. A and B equals to 15 units according to rule 10. A, B in total equals to 16 plus 9, that is 25. So according to the Pythagoras theorem, in this right triangle A and B, AB squared equals to AM squared plus MB squared. AB is 25, therefore AB squared is 25 squared, that is 625. And is equals to AM squared. AM is the missing side, so as it is. Plus MB squared. MB is 15, therefore MB squared is 15 squared, that is 225. So in total, we found out that (625) equals to AM squared plus 225. Here we subtracted 225 from this equation, and finally found out that 625 minus 225 is 400, so 400 equals to AM squared. Here we took root out of this equation, and finally found out that AM equals to the square root of 400, that is 20. So we found out that the diameter of this circle AM is equal to 20 units in its length. If the diameter AM is 20, the radius must be equal to half of it. So the radius R must be equal to AM over 2. AM is 20, so the radius must be equal to 20 over 2, that is 10. So we found out that the radius R of this big circle equals to 10 units in its length. Our mission is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. And therefore the area of the big circle must be equal to pi times the radius of the big circle, that is 10 squared. 10 squared is 100, so in total this expression equals to 100 pi. 100 pi is 314.159. So in total we found out the area of this big circle equals to either 100 pi square units, so in terms of numbers, the area of this big circle equals to 314.159 square units. We finish with the first question. In the next step, I present to you the second question, and we solve the second question in two different methods. In the second question, our mission is to find out the area of this rectangle ABCD. So in the drawing, we have rectangle ABCD, and we also have this semicircle. This is 97 MA, that is equals to 5 units in its length. Again, our mission is to find out the area of this rectangle ABCD. So we started with the first method. First of all those 4 angles inside rectangle ABCD are right angles. We define the center of this semicircle as O. We define the radius of this semicircle as X. In the next step, we join points O and E together by a straight line. OE is the radius of the circle, that is equals to X. Because of the fact that the radius OE is on to point E, that is the point of tendency of tangent DC with this circle, and whenever you have a radius that is on to the point of tendency, then tangent DC will be perpendicular to the radius EO. If DC is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So inside the small quadrangle DEOA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 facing angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this 4 facing angle must be equal to 90 degrees in its size. So inside quadrangle EDAO we have 4 right angles, and according to rule 5, any quadrangle that has 4 right angles must be at least a rectangle if not a square. So we will write to this quadrangle DEOA as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle DEOA, side EO must be equal to the opposite side DA. But EO is X, therefore DA must be also equal to X units in its length. Okay, so in the next step we join points O and M together by a straight line. Point O is the center of the semicircle, point M is the point on the semicircle itself, therefore OM is the radius of this semicircle, that is equal to X. In the next step we find this line segment OB as A and this line segment MB as B. So in the next step I copy this right angle MBO on a new page and implemented the first law and this right angle MBO. Actually this is the right angle MBO that I copied from the original drawing according to the Pythagoras theorem, and this right angle MBO. MO square, this is the square of the hypotenuse, must be equal to MB square plus BO square. MO is X, therefore MO square is X square, and it is equal to MB square. MB is A, MB is B, therefore MB square is B square, plus BO square. BO is A, therefore BO square is A square. So in total, according to equation 1, actually found out that X square equals to A square plus B square. In the next step, I copied this right triangle A and B in a new page and implemented the Pythagoras theorem in this right triangle A and B. Side AB equals to X plus A, side MB equals to B, and MA equals to 5 units in its length according to what is given us in the question. So this is the right triangle A and B that are coming from the original domain according to the Pythagoras theorem. This right triangle A and B, AM squared, that is the square of the hypotenuse, must be equal to MB squared plus BM squared. AM is 5, therefore M squared is 5 squared, that is 25, and it is equal to MB squared. MB is B, therefore MB squared is B squared, plus AB squared. AB is X plus A, therefore AB squared is X plus A squared. So in total, according to equation 2, we have found out that 25 equals to B squared plus X plus A squared. So 25 equals to B squared plus X plus A squared. X plus A squared equals to X squared plus A squared plus 2 times AX. Here we have this equation, this equation 2, we have B plus A, B squared plus A squared. But according to equation 1, B squared plus A squared equals to X squared. B squared plus A squared equals to X squared, so we can substitute B squared plus A squared by X squared for this equation, equation 1. We did it, and I have found out that 25 equals to B squared plus A squared is X squared, and we have also left the X squared plus 2AX. So 25 equals to X squared plus X squared, that is 2AX squared, X squared plus X squared, that is 2X squared plus 2A squared. So in total, according to equation 2, we have found out that 25 equals to 2X squared plus 2AX. Here we divided this equation 2 by 2, and we found out that 25 over 2 is 12.5, and this equals to 2x squared over 2 is x squared, plus 2ax over 2 is ax. So in total, we found out that according to equation 2, 12.5 equals to x squared plus a squared, x squared plus ax. Here we took out x as a common factor from those two expressions, so inside the brackets we left with a plus x. So in total, according to equation 2, we found out that 12.5 equals to x plus a plus x. Our mission is to find out the area of this rectangle ABCD. Actually, the area of any rectangle equals to the length times the length of the rectangle times the width. The length of this rectangle ABCD is AB, and the width is AD. So in total, the area of rectangle ABCD equals to the length that is AB times the width that is DA. AB is x plus A, DA is x. So in total, the area of rectangle ABCD equals to x plus A times x. But x plus A times x is 12.5. Therefore, we can substitute x plus A times x by 12.5. So in total, we should find out the area of this rectangle ABCD is equal to 12.5 square units. We finish with the first method. In the next step, I present it to you how to find out the area of this rectangle ABCD according to the second method. So first of all, you know that all the angles inside rectangle ABCD are right angles. So all those four angles are right angles. We define the center of this semicircle, this point is point O. We define the radius of this semicircle as x. In the first method, I've already proved that dA must be equal to x. Okay, so here we join points, we define this point as n and join points m and n together by a straight line. By doing this construction, we get to do peripheral angle AMN. Peripheral angle AMN is obtained on AN, that is the diameter of the semicircle, and we know that any peripheral angle that is obtained on the diameter of the circle must be equal to 90 degrees in its size according to rule 7. Therefore, this peripheral angle AMN must be equal to 90 degrees in its size. So in the right triangle AMN, we define this angle as alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. 1 plus 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in the triangle. Likewise, in the right triangle A and B, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. In the next step, I copy this right triangle A and N, this right triangle A and B in a new page, and prove that those two right triangles are similar to each other according to angle similarity rule. So those are the two right triangles AMN and AMB that are copied from the original drawing. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus 1 point, therefore they are equal to each other. So we prove that all the triangles of this right triangle A and B are correspondingly equal to all the triangles of this right triangle A and N, and therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AM in the right triangle AMB or side AN in the right triangle AMN equals to side AB in the right triangle AMB or side AM in the right triangle AMN. AM is 5, AN is 2x, AB is x plus a, and AM is 5. So in total, according to equation 1, we can find out that 5 over 2x equals to x plus a over 5. Here, of course, multiply this equation with equation 1, and finally found out that according to equation 1, 5 times 5 is 25, so 25 equals to 2x times x plus a. So 25 equals to 2x times x plus a. Here we divided this equation in equation 1 by 2, and finally found out that 25 over 2 is 12.5, 2x over 2 is x. So in total, this expression equals to x times x plus a. So in total, according to equation 1, we actually found out that x times x plus a equals to 12.5. Our mission is to find out the area of this rectangle ABCD. Actually, the area of any rectangle is equal to the length of the rectangle times the width. The length of this rectangle ABCD is AB and the width is AD. So in total, the area of rectangle ABCD must be equal to the length that is AB times the width that is AD. AB in total is x plus a. And AB is x plus a, and AD is x. AD is x. So in total, the area of rectangle ABCD equals to x plus a times x. But x plus a times x, according to this equation 1, is 12.5. So we can substitute x plus a times x by 12.5. So in total, we should find out that the area of this rectangle ABCD in both methods is equal to 12.5 square units. Okay. Thank you very much.